We have with us an esteemed speaker, Dr. Amit, who brings with him a wealth of knowledge and experience in the field of computer science and engineering. Dr. Amit completed his BE in Computer Science and Engineering with distinction from Karnataka University, Dharwad in 1998, followed by an ME from Panjab University, Chandigarh in 2008. His passion for research led him to earn a Ph.D. in image forensics from Panjab University, further strengthening his expertise in the field. Currently serving as an associate professor at the National Institute of Technical Teachers Training and Research, Chandigarh, Dr. Amit has been a part of academia since 2001. Before joining NITTTR, he gained valuable experience working in the software industry in Bangalore. With over 60 research publications in reputed international journals and conferences, his expertise spans machine learning, image processing, data analytics, and open source technology. He has mentored more than 70 master's students in various research areas and is an active life member of the Computer Society of India and the Indian Society for Technical Education. With such an impressive background, I am certain that today's session will be highly insightful and educational. With such an impressive background, I am certain that today's session will be highly insightful and engaging. So, without further ado, let's welcome Dr. Amit.
Thank you for the nice introduction. Basically, I'm also learning. By default, I'm teacher, but still. Okay, today's my topic is on federated learning-based intrusion detection. This is a very emerging and very important topic. Why this? So most of you might be aware of this federated learning, and some of you might not be aware of this federated learning. So let me give the one concept of this federated learning, why this is important. And as a researcher, as a student, we have a lot of scope is in this. So let me give one example here with the annotation. So kindly confirm me once whatever I'm typing, is it fine? Can you hear me? Thank you.
Yes.
So now let's say nowadays we have a lot of devices across the globe at different locations. So same we will do the implementation the same way. So n number of devices are there. We have billions of mobile devices. Then we have our own personal computer, laptops, etc. So now we need to analyze some kind of malware or malicious activity in that particular device. So as of today now, what we need to do, we have to, let's say we have one central data here. Let's say we have here one centralized IDS system or anti-malware, let's say central anti-malware system. So what we need to do, we need to send our entire data to the central repository and they will analyze the malware. So here we have two issues. One is of the latency because we have to send the entire data. That is the one issue. Second issue is that of the privacy. We have to share our data. That is another concern. So how to overcome this issue? This issue we can overcome with the help of federated learning. So what federated learning do? Instead of sending the data to the central repository, we will run the anti-malware or machine learning or deep learning based models here. So let's say machine learning based algorithm all over this, and it will not send the data. It will train the model based on the existing data, and it will send only the weights and gradients. Weights and gradients. So in this way, we are able to preserve the privacy and the latency of the network. Weights and gradients. Similarly, here on from here. So this is the main concept of the federated learning. Now we'll see here. So federated learning is just like a decentralized approach. So where multiple clients, multiple organizations, they can collaboratively train the machine learning algorithm model while keeping their data localized and private. So now here only the model update, that is gradients, are shared with the central server, ensuring the data privacy. This is the main concept of the federated learning. So in Python there are n number of libraries are there. So that also we'll see, and we will use the TensorFlow for the implementation. So this is a like a machine learning approach that train model across the multiple decentralized devices or servers without sharing the data. So it enables the multi-party collaboration, enhance the privacy, enhance the security, and save the bandwidth also. So what is the core techniques are there? So there are two core techniques are there. That is the federated averaging and differential privacy. So why federated learning for? Yes, please. So why federated learning for threat analysis? So now in traditional machine learning algorithms, it involves the sending the user data, as I told you, to the central server for model training. So which raise the privacy concerns. Whereas federated learning allowed training model locally on the end devices or end user devices, sharing only the model updates and not the data. So that enhance the user privacy while maintaining collaborative learning also. So now, why federated learning for threat analysis? That is the topic of today. So it preserves the privacy. So now data is shared and protect the sensitive user data. And there is a concept of decentralized data. So that leverage the data distributed across multiple organizations or endpoints, and collaboratively threat detection can be enhanced, or it can be done, and enable the entities to collaborate on threat analysis without exposing proprietary or sensitive information. So what are the key uses in threat analysis, like antiviruses, anti-malware, intrusion detection system, denial of services, or any? So under malware, we can train the shared model. So we can use the logs from different organizations without sharing their data and detect the patterns in the behavior of the file or the network anomalies. And we can identify the unusual patterns in network traffic using federated training on data from multiple endpoints. So what are the key uses in like phishing, email detection, fraud detection, endpoint security? So a lot of in various fields we can deploy this. So these are the main components of a federated learning system. So we have the endpoints, we have the central server that aggregates the model update from client and update the global model. And we have the local model training on the each client, and then we do the federated averaging, combine the model updates from client into global model. So now, before showing the demo, let me show you the data, and all of you can download from the Google Classroom this data set also. So here now I'm showing this is the data set. So here you can see we have I have taken here 5 training samples from to demonstrate from the like 5 remote sites. So if we open this file here, so now you can see here, this is the file, and lot of features are there. Approximately 196 features are there. And in the last, you can see the label where it is mentioned here 1 or 0. So 1 shows it is a malicious, and 0 shows the normal traffic. So similarly, we have 5 files for 5 different locations, and we have the test data set. So now this is our test data set. And in this test data set, you can see again, there are 196 features are there without the label. So this data we will use for the testing the or for the finding the performance of the model. So test data is always used for the performance of the model. So now there are various Python tools are available for federated learning. One is the popular is the Flower. So it stands for Flexible Federated Learning Framework for Experimentation. And also in the TensorFlow federated framework is available. And also PySwift is also available. And OpenFL is also available. So we can use any of the library. And for this demonstration, we are going to use the TensorFlow. So now we are going to use this data set. This data set, we are using the network traffic for intrusion detection data set. And we can use the CCIC. These are the benchmark data sets. Or for phishing email detection, we can use the email phishing data set. Or we can use the custom logs also. Or we can use the custom logs also. So for now, these are the implementation step. First, we'll do the pre-processing. So we will split the data set across the multiple clients to simulate decentralized data approach. Then we will define the model. There we will see we will define our own neural network based model or random forest or depend on the or any other model we can deploy. And then we will set up the federated learning. There we will train the model locally on each client, and we will use the federated averaging to aggregate the updates. And finally, we will evaluate the global model. So global model will test the global model on a centralized validation test data set to evaluate the performance. So these are the example code. So just like we use the scikit-learn, Python various libraries like pandas, numpy, matplotlib for plotting. Similarly, here we will import the flower as FL as an abbreviation, and then we can start working on this. We can import the predefined models like random forest, and then we can simulate the client function. We can so with this data set we can split and train the model. So this is the example of the federated learning at the client side. So we can define the function, and now we can capture the training data, training label, test data, and test label. And then we can use them. We can fit the model. We can train the model with training data and training label. And then we can evaluate the performance. So in this way, we can do for all the clients and then send those trained model to the central server. Then we can run the federated learning. Now we'll see in the implementation and demonstration. So now the data set that we are going to use is a well-known cybersecurity data set that was created by the University of New South Wales, that is also known as UNSW_NB15. So it contains real and synthetic network traffic data, including normal and malicious activities. And this is widely used in education and research, and also for developing intrusion detection systems. It consists of normal traffic, it consists of malicious traffic, and various features. So approximately 196 features are there, consisting of source IP, destination IP, and attack levels. So this is a subset of the training data, and so it consists of around 196 columns network, and that consists of the network traffic characteristics like protocol, what type of protocol is there, what is the port number, what is the source port, what is the destination port, what is the flow duration, source IP, destination, and at the last we have the target value or the label. So label will represent whether the traffic is normal or malicious. So the features are there, even about the start time and time of the flow, duration of the flow, how many number of bytes content contains, packets, flags, all the network information is there. Then we do the scaling to normalize the features for the better efficiency of the model. And also we are using that because it is a time series based. So we will use the time lag data to reshape the data into a sequence of historical traffic patterns. And traffic is labeled into attack categories, including, so there are various tools are available. Even using these tools, we can generate the massive network packets, like users are to find the vulnerabilities. There are various tools are there to uh, create the environment of denial of service attack. There are malicious access points are there. Several exploits are there in the software. So, so what we will do in federated learning, we will train the each subset from different organization or different clients, and we will understand which features are most indicative or malicious in nature. So after loading the data, we will do the pre-processing to handle the missing values, and we'll scale the features also and split the data. So then we will define the model. So now it's up to our end how what type of model we want to define. So in this implementation, we will use the dense neural network, which consists of input layer, output layer, and the hidden layers with the activation function as ReLU. And at the last, because it's a binary classification kind of problem, so we can use either softmax or sigmoid. If you have multi-class predictions, so for example, you have multi-class, so you should use a softmax. Or and for binary, you can use softmax as well as the sigmoid. Then we'll have the model. So uh, we will set up the different clients. We'll train the locally on subset of the data, and then after training, we will send the data to the central server. So central server will combine the updates using the federated average. So now clients will train locally, then we will do the aggregation, and finally we'll get the output in terms of loss and accuracy. So our objective is loss should be minimized and accuracy should be maximized. And then we can evaluate the model in terms of accuracy, precision, recall, and F1 score. Now these are the steps. So first we need to import the essential libraries like TensorFlow, NumPy. Now I'm opening here the source code. So this is the pipeline. So here first we need to import the libraries like TensorFlow, NumPy, etc. Then we need to upload the dataset. Or now in my case, we have a large amount of data, so I have uploaded in the Google Drive. So today we'll see how to bind the Google Drive with the Google Colab. So we will load the dataset. We will do the pre-processing and split the dataset into training and testing. Then we'll define the model, the architecture, and we'll get the summary of the model. So we can simulate multiple clients with local datasets. We will implement the aggregation logic for combining the local model updates, and then we'll display the initialization and client configuration. And finally, we will do the federated training. We train the model in the federated settings for multiple epochs we can give here, and it will show the loss and accuracy matrices after aggregation. And so now I will show you the demonstration here. So after that, we'll discuss about the observations and what is the future scope. So kindly confirm me, if the font size is fine or shall I zoom it? So this is the pipeline while implemented the federated learning based IDS. So first we'll do the load the data set. So we can load the data set from Google Drive or from cloud storage. Then we will verify the data set and its integrity. We will split the data into training and test. We will normalize the data, that's a part of the pre-processing. We will define the time lag because we are working with the time series data, and it is useful for time series based model like transformers are there nowadays, LS team, GRU, etc. And we can reshape the match. We will reshape the data to match the input format requirement. We can select any of the model. So there are n number of models are available. So we can select any of the machine learning model, or we can define the model architecture and compile the model according to the proper with the appropriate optimizer and loss function. So on different client we have to do the local model training. So we will assign different model. Even we can use different model or same model to different remote sites or different end users or edge devices or on the local servers. Then we will train the local model independently on their respective dataset and save the trained local model for aggregation. Then we will apply the federated model aggregation. We will upload the trained local model to a central federated server. And then there we will aggregate the model using techniques like federated averaging. And we will compute the global model by averaging weights from the local models. Then we will deploy the aggregated model. We will distribute the updated global model to all remote sites. We'll deploy the model in real time for intrusion detection and monitor the system performance also. And finally, we will evaluate the model in terms of the performance matrices. And further, we can do the optimization and continuous fine-tune the hyperparameters and continuous learning we can perform. So this is the pipeline to implement the federated learning. So now this is the first step. So this is the main and the step one where we are uploading the data. Upload the data. So we can upload the data either from this side also on the left panel, and now on the right side you can see it is connecting to the Google Colab, and you can upload from here, or simple you can say from google.colab import drive, and simple you can mount the drive.mount content drive. So once you run this, it will ask for the authentication. So now it is asking permit this notebook to access your Google Drive. So we'll say yes and connect to Google Drive. So now it's asking my username. So already I have logged in. So now it's giving the continue and giving the permissions. So now it will take few seconds. Now it is showing here mounted at content drive. So we can verify also. So we can run the list command to see the content of the drive. So I have given the full path here, /content drive, my drive, collab notebooks under this federated learning dataset. So there you can see there are 5 datasets are there with the name train 201, train 202, 203, 204 and 205. So we will have the deploy as a 5 remote sites for the demonstration purpose. For site 1 we will use the train 201. For site 2 we'll use the train 202. For site 3 train 203, and for site 4 train 205, and for the site 5 we'll use this data for training the model. And this is a standard for the test data. So now we are creating the list of directories. So here we are using the, if you are aware of the basic data types of Python, so here we are using the list. So where we have defined one variable directories. And using the OS library, we are going to make these three server and central server. So now we can, it is showing directory data, directory server, and directory central server created successfully. So after creating the directory, so for directory in directories, we are using the os dot make directories function, and we are able to create, and we can verify it also. Now, why we have created these three data sets? Because I want to copy all my data into this folder for here. Instead of typing it again and again, the full path, content, drive, my drive, collab, notebook, instead of giving the complete absolute path, so simple we'll use the data folder. So just we will use the command copy. This is the Linux, because this machine is a Linux, as I told you. So we can again verify by which command, lsb underscore release minus a. So they are using the one of the Linux variant by the name Ubuntu. So we can run any Linux command. So this is a Linux command. Copy the Linux command. Recursively copy all the file we have given here, star into this folder, and we can verify also. So now this data, 5 training data and 1 test data, is now copied into the data folder. We required another Python file. This is the data preparation file. So we will upload from here. We can select the file. So there is a data preparation.py file is available. So let me show you the code. This is the file. So it is using the NumPy file, and we have defined our own functions. The load CSV, then data pre-processing, and in this size append the data size and features we are getting here in the return the features. So this the so there are two functions are there under this load CSV and data preparation. So now here we have uploaded this file, and now we are importing some more libraries like NumPy, Globe, OS, sklearn, pre-processing. We are going to use the min-max scaler, then Keras, TensorFlow, and to suppress the warning, we are using the warnings, and from data pre. So data pre is this file. It is not part of the Python, but it's a custom file. And we are importing the functions load CSV and data preparation. And we are specifying the number of time steps for time series or sequence length for time series data. So now it's running. So now already the definitions are also mentioned here. Like what Globe will do, it is used to find the file path and to match the specified patterns. So in our case, we have all the files in CSV format. It is in the CSV format. It may be in CSV format, it may be in Excel format, or maybe in other different format. So what we'll do here, we will find all the CSV file in a folder, and then we'll do the pre-processing accordingly. Then NumPy for the numerical computations, and it is used for multidimensional array and perform the mathematical operations very efficiently. So simple, we'll say from this import the path, and regarding OS we will for the directory path. sklearn is from sklearn pre-processing, we are calling the pre-processing tool or the min-max scaler. What it will do, it will scale the numerical value to a particular range in between 0 and 1. We are importing the backend function of Keras, which provide the low-level operation for deep learning or neural network-based models. And TensorFlow is again application program interface API to for the building and training the deep learning model, and warning model to suppress the any warnings. And we are also importing two functions from the local file. These functions are used for loading and pre-processing the data set. And here we have set the value uh, time series lag value. This is known as time series lag value. That is a kind of sequence of length 4 when we process the time series dataset. So in time series dataset, this time lag, we can have any variable name. So for demonstration purpose, I have used the TL, any name we can define. So TL will define how much historical data to be considered for each prediction. And so in this context, this time lag is often used to define the time window length, meaning how many past time steps are considered when making a prediction. So we have taken the 4. So it suggests the model using past 4 time steps to predict the next value. And this is very common in recurrent neural networks, sequence model or for forecasting, or when we are dealing with the time series data. So like we want to predict the stock price. So there also we require the past, how many days we want to use to uh, predict the price or the stock price. So here 4 will represent the, we are using the past 4 days of data. So 4 TL4 means it is considering the 4 historical data or previous steps. Now we will start from here. This is the client 1. So this script will load a data set of 196 features and one label. And then after loading, it will do the normalization. So in normalization, the numerical values will get converted into in between 0 and 1. And we are using the time lags of 4. So it will create the sequence of 4 time steps. And that will help the model to learn the patterns over time. And this uh, time lag series is useful for the model like GRU, LSTM, even transformers or time series dataset. So now in here you can see the code in remote site 1. So we are using the dataset. So instead of writing the complete full path, absolute path, so now just we have to write data slash that particular file name. So because of this reason, we have copied the data in the folder data. So here we are using the train dataset train 201, and here we have specified the path, and we are using the load CSV, or we can directly use a pandas read.csv also. Then after loading this, we are converting uh, into the min max scaler. So here we have specified,
Chimisa,
yeah,
so there is a disturbance.
just 1 second. So now I hope this is fine now. So here now we can see we have taken this data set in remote site 1 we have considered. So for the demonstration purpose, I am considering the 5 different sites, and we have load the data set. So we can load with the help of pandas also. And then we are training the data set here. These represent the all rows, and these are the column 0 to 196. So for example, here. Let's say here I have feature 1, feature 2, feature 3, and this is my output. So here how many features are there? So total we can say, or how many columns are there? How many columns are there? There are 4 columns are there. So out of 4 columns, 3 columns contain the independent variable, independent value, or the features. And the last column, or the 1 column, consists of the label. So what we are going now, we are segregating the features and the label. So here what we have defined, so let's say this is my in a variable A. So here I am defining column all rows. So first we'll define the all rows. Column means all rows, and from 0 to suppose if I write here some number 3, 4, 5, 1, 2. So index there are 2 type of indexing in Python. One is in the forward direction and one is in the reverse direction. One is in this direction, another is in this direction. And the index here start from 0. So 0, 1, 2, 3. And in this direction, it will be -1, -2, -3, -4, -5. When we are saying a subscript from 0 to 4, so it will exclude this number and will get the output as 3, 4, 5, and 1. 0, 1, 2, 3 index. It will exclude this one. So similarly here, when we are saying here in this code 0 to 196, so it will exclude this one and accept the 196. All the features will come in this variable, and then we will do the scalar dot fit. We will use the min max scalar. We have called this function, and using we have instantiated in the variable scalar and scalar dot fit, and we are passing this data because we have captured the entire data, all rows and the which columns from 0 to 195. The data from 0 to 195, except the label, all features are there. And then we are doing the transformation of this, and after transformation, like if you see again here, if I show you this data set 201, 201, so there are certain values you can observe 1062, 200, 200, then 26,000 something. So all these will be converted into a common scale, and all these values will get transformed to the value in between 0 and 1. In between 0 and 1. So this is also required because of the if we don't do this one, then we may get the poor performance in our model. Then we are doing the pre-processing on this data set, and we are training this. Now let me run this. So now you can see, so the part of the code process data for the remote site 1, multiple data sets for different data sets are being used. So this trained data set extract the first 196 column, and so in the column number 196 we have the feature how 196, so that means 0 to 195, 0 to 195. So this likely contain the feature used for model training, such as network traffic statistics could be there. Then we are using the min max scalar to scale all values to the range in between 0 and 1. So with the common scale, it will help the model for the training purpose. And as we are aware, fit function is there to calculate the necessary scaling parameters and transform, apply the scaling to the data. We can prepare the training data sequence creating using the time lag. So there we are passing here time lag. Here, if you have noticed here, we have passed here the time lag. So it will likely prepare the time series data set, and it will group the data into a sequence of 4 consecutive time steps. Then we are doing the reshaping the data sets. So we don't know how many rows are there. So we are giving the -1, reshape the data into a 3-dimensional array. So -1 will automatically determine the number of samples and the number of past time steps, and 196 the number of features. Similarly, we are preparing for the site 2 here also. In the same way, we are reading the training data 202, and so quickly I will do for second, third, and fourth and fifth. So now I'm reading here. This is the same concept with the site 2, so data is ready. Now here we are doing with the remote site with the third number, same with the fourth, and same we are doing with the fifth. So I hope now you got the idea. So data is ready with the 5 remote sites, and then we have one test data set. We have separately we have taken in a variable test path, and also we are doing the scaling of this. And if you want to see the data here again, let's say I will show you about this data, so all of you will get the idea. I am printing this, so you will see here it is a range in between 0 and 1. Similarly, here when we do with the labels, so it consists of the label either 1 or 0. Now similarly, when we are doing with the test data set, we are reading this test data set, and original data set is in this variable. So when you print this, it consists of the CSV file, and after loading this, then we are performing the test data scaler, and in this variable you can see these are the values are available, and now after converting into the and reshaping this, we can see the test data set is also in the same scale. Now what we are doing, we are matched the weights here. So we have to match the weight file. So in the server, when we call the function, so here we are defining the function load models, and for weight path in the models, we are defining the one architecture of the model, like here convolution of one dimensional with the various filters, kernel size, activation function. Here you can see here. So here we have defined the architecture. So you can see here we have defined the architecture. TensorFlow, this is the sequential format, and we are giving the input shape is equal to time lag we are defining, and the shape we are defining, and we are defining the convolutional first dimensional, we are passing the filters. So in the initial layer, in the low level, there is a less information. As we go from low to higher level, there are more information. So because of that reason, we have taken in the middle layer and the higher layer, and 128 number of filters we have taken, and we have taken the activation function as ReLU. What it will do, it will convert any negative value to 0, and maximum value will be as it is. So for example, we got two numbers, -5 and let's say 7. So output will be 0 and 7, because it will convert any negative value to 0, and maximum value as it is. So now we have deployed this convolution layer, and then we have done the flatten and dense in this model. And finally, because it's a binary related problem, so we have used the sigmoid. And in case if you have multi-class, you can use the softmax also. Then we are compiling, because it's we have only two outputs in the our label, malicious or normal. So we are using the binary cross entropy, and we are using the optimizer and the matrices as accuracy. So now this is the function here, define load function. When we call this function, it will run and pass the values accordingly. So it will find all the saved model file in the server folder, define the deep learning model, that is a convolution neural network for time series. We have defined the one-dimensional, and for images we use the two-dimensional. We have load the pre-trained weights into the model, extract the model weights, and return the model weights. So now the function is ready. So here, one by one, now we will define the model for remote site one. So what we'll do, we are calling for the in the previous case we were ready with the data. Now what we are going to do, we are deploying the model. So you might have noticed that in site number 1 here, in site number 1, we have captured the data into these variables, x train 01 and label in the y train 01. Similarly, for site 2, we have taken the data in the x underscore train 2 and label in y train 2. Same with the third one, and same with the fourth and fifth one. So now for this model, when we have to deploy this model for site 1, we require the site 1 data. So we can do on the same cell also, just for the better clarification. Now we are defining the models. So we are passing the train 01 and the train label, and we are defining, and this consists of entire features, and this consists of the labels, and we are defining these parameters, and we are saving by the name fl model dot h5. And now this function is ready. Same we will do with the second one. So what it will do, it will check if any pre-trained model is exist in the central server. If that model is available, then it will load that model and recompile it. Else it will create a new model from scratch, and it will ensure the training and test data size match to avoid the errors. Then it will train the model using the provided data, batch size, and number of epochs. So as we have discussed yesterday, so what is batch size? What is number of epochs? So here, again, I'm defining here. What is the meaning of batch size? These two parameters are very important. So we should use a batch size in the 2 to raise power some number. So it could be 4, it could be 8, 16, 32, 64, 128, or more, 256. But batch size. So if we take 120 or 256, it will take a lot of memory. So there is a memory constraints. So there is a memory constraints are there. So depend on the amount of the data. It is, if you have less amount of data, you should go for 16. Or if you have maybe in few thousands, you can go for 32. And if you have more data, you can go for 64. So what it will do, so let's say you have 400 samples. and you have taken batch size as 16. So the number of iterations. No, iteration is a different and epoch is a different. So when entire 400 sample pass through the model, that is known as one epoch. One epoch. One epoch. And number of iterations will be 400 divided by 16. So it will be, I think, 25. Yeah, it will be 25. So 25 iterations. So for one epoch, it will take 25 iterations. 25 iterations. So for a good, for the better learning, we must have whether we can go with the 10 epochs or we can go with the 20 epochs. And we should not give more numbers. Sometimes some researchers, they give 100 epochs. So the problem could be there. It can learn the noise, and there may be the problem of overfitting may be there. So there we can do the early stopping is the one criteria. We can deploy early stop criteria, or we can take the appropriate number of epochs. So when in this way we can train the model, so we can provide the data, batch size, and the number of epochs, and we can save the weights. So as I told you, we are not passing the data. What we are training, we are after training the model, we are sending the weights. So there we are defining the model. So this function takes the training and test data, and it will take the number of features that per time be required, batch size, and the number of epochs to train the model. So these are the necessary libraries we required, and then we can recompile the model, and we can ensure the data consistency and train the model, and finally we'll save this. So here, so here, so in this way we can save it. So now in the same way we are now defining the model for the second remote site. So here the same model we have defined here, and similarly we are doing for the third one, fourth one, and the fifth one. Fourth one, and we can for the site number 5. So now up to here, what we have done so far. Up to here, we have considered five remote sites. We have prepared the data set. Prepare the data set for each remote site. So we have done for site number 1. Same we have done for the number 2, 3, 4, and 5. Then after that, we have now prepared the model again for all the sites one by one. We have prepared the model. We have prepared the model for each remote site. So we have done up to here. So now after this, now we are going to use the function load model, load the weight for all the models that is in the server directory. And we are initializing the empty list to store the weight of each model. Here. Store the weight of each layer for each model, and we are defining the convolution layer. So now in the same way, now we are going to perform the average the weight of the loaded models. So up here, just we have defined the functions. We have defined the functions here, and it will iterate over each layer. And now we will build the model. So here we are defining the build model, and finally we are doing one function to evaluate the model. So we are getting the score and we'll print the score. And we are defining the saved function, and then this is the working flow. So if you see here, because up to here just we have taken all the as a function. We have taken all everything as a function. So just for better clarity, I am mentioning here what are the functions we have used so far. So here just we have called that the data, and that is in the these variable train path underscore 01 y train x train, and same we have done with the remote site 2, remote site 3, remote site 4 and 5. We have not used any function here, and this is our the test data, and we have done the scaling. So one of the function we are using the load models. We have used the functions we have used. So functions we have used like here, define the load models. So here what we have defined the architecture of the model. We have defined the architecture of the model, and same we have done with the after defining the model, we have defined the NITS for site 1. We have defined another function, define NIDS model 101. And in this model, we have defined the, we are calling the model and we are compiling it. We have defined the model, we are compiling it, and we are initiating the and training the model and saving the weight in this. Same we are doing with the at site number 2, site number 3, 4 and 5. So same we are doing with the model 2. So instead of writing this, and same with the third site, fourth site and fifth site. So here model 3, same we have done with the model 4, same we have done with the model 5. And then we can define the load models. Here we are defining the function. This already we have defined the load models. And we are calling another function, getting the average. So here and then we have defined the build model. We have built the model, and there we are passing the average weights, and then finally we are doing the evaluate the model and save the model. We have defined the model. and we are saving them. We have evaluated and save the model. Now this is the working flow. This is important here. So if you see the model here, we are calling all these functions here. So if you see the working, we have defined the model flow and we are calling the FL average, which is defined here. We are calling this function. We have defined the build model. Again, we are calling this function and we are calling this evaluate mode model. So this is the function and we are saving the FL model. That's it. We are calling this. So this is the main working flow. So here we are calling this FL average. That is also we have defined here. So these models we are calling here. FL get the average weights, build the model, and evaluate the model and save the model. So now we are running this. Now it has creating. Now we are calling this function as a in this. So we now, if you have seen here, we are calling this model 1, 2, 3, 4, and 5 with the data, and we are giving epochs. Maybe we can give 3 epochs or maybe 5 epochs. But at least we can give up to 20 epochs to optimize the time for the online session. Just I've given the less number of epochs, and we will print, and we are calling this model underscore FL. What it will do, it will call this function model underscore FL, and automatically it will call these functions, and this function, let me show you here. So now this is the final output and final results we'll get here. What we are doing, we are calling this model. Now we are in the epochs, we are calling this model, and I have specified the epoch number as 5. And in this, we are calling this function, and the save function, which is already defined above. Model function, evaluate function, and save function. So this is the final flow. So this is the final flow. So now when I will run, it will start working on this model and it will give the output. So now we have taken the 5 blocks. So now it is defining the NIDS model 1 with the train data, train label, test data, test label, and we have defined the shape. It's training the model, and you can see here it is showing start working with the loss function and the accuracy function. So now finally we will get the 2 values. So first value will represent the loss. That is we have used the binary cross entropy loss for the classification problem, and it should be less. It should be minimized. So lower value will indicate the better performance, and the second parameter will show the accuracy. So we have to get the maximum value here. More the value, better is the result. So in this example, easily we can find out 0.1734 represent the lost value, and 0.91 or 91.91% is the accuracy. So there are various loss functions are there that we can do. Now we are using the binary classification. We are using the log loss or binary cross entropy. And when we have to use the multi-class, we can use the categorical cross entropy. And if you are using some complex space like a sport vector machine, which encourage the margin between different classes, so there you can use a hinge loss. So when you are working with the binary classification problem, you can use the binary cross entropy loss function. And when you are working with multi-class, you can use the categorical cross entropy. When you are working with multi-class and integer labels are there, you can use a sparse, categorical, cross entropy. And for regression, you have both options, mean absolute error or mean square error. If you have few outliers, you can use the mean square error. If you have many outliers, you can use the mean absolute error. And for SBM, you can use a hinge cross function. And for probabilistic model, you can use a KL divergence. So again, all of you can refer this website here, papers with code.com, papers with code.com. You can see here the methods, attention method, activation function, regularization method under as per your area of interest. So now we have worked with one type of sequential, because in network flow the data is coming in the time based and in the sequential form. So again there we have under recurrent we have LSTM, GRU, convolution and pointer. Then we have time series related different methods are there, bidirectional recurrent neural network, multiscale, time delay, and many more. And today we have discussed about the federated learning or any topic you are doing research or project, federated learning, if you write here. So you can see there are few papers are there as compared to the other methodologies or other methods. Only as of now it is showing 1640 papers with 12 benchmark and 11 data sets are there. So this is a kind of a machine learning approach that allow multiple devices to collaboratively train a shared model without exchanging their data. So it's a very promising area, and I advise all of you should at least do something because the code is with you. You can publish the results, you can do various experiment with this. So it is a very good and very novel approach to train the model without exchanging the data with each other. And instead of data to the central server for training, the model is trained locally on each device. And only the model updates are sent to the central server, where they are aggregated to improve the shared model. So this approach allows the privacy-preserving machine learning, as each device keeps its data locally, only share the information needed to improve the model. So here also you can get the paper and codes are available. Here, like related to the C4 data set, and very few paper are there with related to the intrusion detection or with the malicious code. So even for mobile devices, for malware detection, one can adopt this federated learning approach. So now we'll see the final result with 5 epochs. So now you can see here in the first iteration, the first epoch, we got this much accuracy and this is a loss. And again in second epoch, we got accuracy of up to 99% and loss is 0.018. Then epoch 3 and then epoch 4, and because it's starting from, we have given the 5 epochs 0, 2, 0, 1, 2, 3 and 4. So finally we are saving the result, and finally we got the average score of 0.20%. 203 is the loss, not percent, but 0.203, and 0.890 is the accuracy. We can save and we can do the average of these. So for further improvement, we can give more number of epochs. So now I will revise. I will describe it again once. So meanwhile, if any participant has any doubt, question, query, feel free to ask. So what we have learned, we can, what is the summary? We can evaluate the federated model on the test dataset, save the centralized model for further use. We can train the loop, we can run for multiple epochs, where each epoch contain the local models, aggregate the weight into a global model, and evaluate the outdated global model. And finally, we get the output in the form of training loss and accuracy. So now this code demonstrates how federated learning enhances data privacy while building robust model for intrusion detection systems. So what are the observations here? So federated learning ensures the privacy with good detection rates, and discusses the federated learning and its application to intrusion detection systems. It emphasizes the privacy preserving techniques, and also it minimizes the communication overhead because it does not send the entire data set. And client could be of different nature. Maybe on some may be using Mac operating system, some might be using Linux operating system, some might be using Windows operating system. So it can handle client heterogeneity, and they can use different models also. So what is the feature scope? So for optimize the communication and for differential privacy. So there is a good scope, and it minimizes the communication overhead between client and server. It handles the non-independent and identical distributed data across the client, and use differential privacy or homomorphic encryption to enhance the privacy regarding to the security. So there are various real-world applications are there, like cyber threat intelligence sharing are related to antivirus and malware, or collaborative learning among organizations, decentralized fraud detection, cross-industry collaboration, endpoint security, and protect the edge devices using the federated learning. So if we see about the current state, so it's continued to evolve with application in healthcare, finance, and smart devices. So in healthcare, collaborative diagnosis model across the hospitals can be deployed. And in finance, fraud detection without sharing the sensitive transaction data. And in smart devices, enhance the personalization in IoT devices. So future directions are there: federated transfer learning, personalized federated learning, scaling these systems, or one can propose this concept or enhance this concept to handle the millions of devices. So what we have done so far today. So quickly, I will revise before that. Any question, query from any participant? Okay. So if there is no question, query, so what we have learned today. So for federated learning based intrusion detection, why this approach? Because this approach train the model without sharing the data. And this is a decentralized approach where multiple clients can collaboratively train the model without sharing the data and keep the privacy. So this ensures the data privacy, and this concept train the model across the multiple decentralized devices or servers without sharing the raw data, which enable the multiple party collaboration and enhance the privacy and security. So the core techniques are involved in this are federated averaging and differential privacy. So why federated learning for threat analysis? Because traditional models or traditional approaches, traditional techniques, they have to send the data to the central server, which raise the privacy concerns. Whereas in federated learning, without sharing the data, we can train the model and only share the model updates. That will enhance the user privacy while maintaining the collaborative learning. So why federated learning for threat analysis? So it will preserve the privacy preserving, protect the sensitive user data, and it's a decentralized approach. It leverages the data distributed across multiple organizations or endpoint, and it can be enhanced using the collaboratively threat detection techniques. So enable the entities to collaborate on threat analysis without exposing proprietary or sensitive information. So what are the key uses? It can be deployed for malware detection, intrusion detection system, phishing email detection, fraud detection. So like there are multiple banks, so they need not to share the transactions or the data. So it can be used for the fraud detection and for the endpoint security. Now people are talking on IoT, industrial IoT. So it can be deployed at the endpoint also to mitigate the vulnerabilities. So what are the components are involved in federated learning? The clients, central server, local model training, and the federated averaging. So for demo setup, there are a number of libraries are available, and one can explore on the official website also, pypi.org.
Good evening, sir.
Yes,
So, as you said, in federated learning, we all the devices need not to share the data, but they can train model locally, right?
right,
So that is what I have got from the
right,
session.
right, right.
है ना? So the my point is, if we need to when we need to train any model, we need to take up the data. But if we are taking the data locally on the device and we are training so all the devices might have got the different models for different data. Am I right or wrong?
Different models. Yeah, yeah. For let's take an example. Let's say, uh, are you able to see this notepad?
Yes, sir.
Okay. Let's say we have 10 remote sites,
Right, sir.
and they maybe, uh, let's say, example of banks. We
Mm-hmm.
have different 10 remote sites, 10 banks are there.
Mm-hmm.
And so I'm rotating with bank 1, bank 2, and bank 10.
Right.
So they may use a model. Then now it's up to them. They may use a different same model or different model. Let's say bank 1 has used the model 1 because they have different type of data set.
Right.
Amount may be different. Amount of data may be
Mm-hmm.
less amount, maybe in few GBs,
Mm-hmm.
few GBs. Whereas another bank which may have in the data in terabyte. So naturally they have model 1 may not work there. So they may use a model 2. And similarly, bank 3, bank 4, they may use the same or different data set. So this is the terabyte. For better clarity, this may be in the terabyte. This is the model 2, and this is the model 1, model 1. And let's say again it is using model, maybe model 1. Is it clear up to here?
Right, sir.
Now what they have to do, once they are, what it will contain? It will contain the weights and gradients. Weights and gradient. Gradients are just
Yes,
like
sir.
the feedback, weights
Yes,
and the
sir. Yes.
gradients.
Mm-hmm.
It will take the gradients, weights. So it will pass only the weight and gradients.
Mm-hmm.
It will pass the weight and gradients. So again, I will show you these things. So they will only pass in the weight and gradient. They are not sharing the data.
Mm-hmm.
And all these are going to the central server.
Mm-hmm.
Then central server, they will use a averaging system. So like there are antiviruses companies are there, anti-malware are there. Like
Mm-hmm.
in our mobile, we have millions of mobiles are there, and all of us has, let's say, installed some antivirus,
Mm-hmm.
any antivirus. So that antivirus will not take our data. It will do check there on, and it will send only the weights, the trained model. And in federated learning, that's why it is mentioned here, uh, in the federated learning, like here in the beginning. So federated learning is a decentralized approach where multiple clients, they can maybe or may not be collaboratively or maybe independently train the machine learning model while keeping their data localized. Only the model updates, weight and gradients are shared. So what is shared with the central server? Gradients and weights are shared, ensuring the data privacy. This is the main concept of the federated learning. Is it clear?
Earlier in the Python, we used to keep our weights according to the data set we are choosing, right? So
Okay,
earlier, what exactly we did in our previous machine learning models is whenever we are taking our data set, we decide weights and gradients according to the chosen data set. Now,
right,
as you said, our data set is locally set up over there in our devices. Like
right,
we have different devices from location one L1 to L10. We have
right,
10 locations at 10 devices, and we are keeping our data locally
right.
in those particular devices. So if the data is localized, then the weights and the gradients can also be kept locally, and they, although they may be shared with the central server, but my point here is what is the point of sending the weights and the gradients to the central server, because they are of no use to the central server, because they are decided on the local basis, local device basis.
Yeah, I got your point. So now you can see here when we have multiple devices, like in multiple banks or multiple. So what federated learning will do, like here you can see here. So one thing is clear to you now, it raises a privacy concern. We are not sending the data, and you can deploy the existing machine learning model also. There is not
That is right, sir. That
right.
is right, sir.
So this is a concept to share the weights, and after that they will analyze these collaborative with this. They will analyze what type of threat is there.
Mm-hmm.
For example, if there is any kind of denial of service attack or zero-day attack, when you will learn more sessions, you will learn different type of attacks are there. Denial of service attack, intrusion
Okay.
detection system attack. So
Okay.
your that model may not be sufficient. So it has to be go for the further analysis.
Okay.
That is the main aspect of the federated learning.
Okay.
So that's why the key uses in threat analysis is related to the malware detection
Mm-hmm.
or intrusion detection system or for phishing email detection. So there may be possibility your model may not be able to catch that attack. So it will enhance the knowledge at the central point because they are rule based. Some are different. So it will enhance in the for endpoint security in this way. They can mitigate the vulnerabilities.
Okay.
So that's why these are the components. So
Mm-hmm.
you are right that at the client's weights will be there. Then what is the use to send to the central server? So central server basically aggregate these model updates
Mm-hmm.
from whom clients, and
Mm-hmm.
they update the global model also. So
Mm-hmm.
finally they are learning. Basically, uh, it's becoming more intelligent because let's say there are 10 locations,
Mm-hmm.
and at 10 location different type of attacks were there.
Mm-hmm.
So if they are working individually, then the model is not getting that knowledge or it's not learning. So
Mm-hmm.
from 10 different sites, when it go to the central server, it will aggregate the model updates and it will update the knowledge of itself also. It will update the global model also. So
Mm-hmm.
what will happen? The central server will become more strong.
Mm-hmm.
That is the main focus of this validated learning. Otherwise, no use of this. It is
Yes.
not. It is not just simple collection of the weights. It is updating the global model also.
Right, sir.
So
Thank you
client
so
train the
much.
yeah. So client train the model locally on their private data, and
Mm-hmm.
Federated combine the model update from various clients into the global model. So finally, what we are doing, we are empowering the global model.
Right, sir.
So tomorrow again, if there any kind of attack happens, so easily it will find out as compared to the various locations, because various IDS or anti-malware are not that much strong.
Right, sir.
So as compared to the global model. So
Thank you so much, sir.
welcome. So now here you can see I was showing you not only these libraries. There is an official website here, py.org. And when you write here simple, you might be working with blockchain, quantum computing, or hybrid approach, or if you say federated learning. So you can see like in 2024, federated learning framework is there. Learning server is available for data intern, Mindspore federated, PyTensor federated. These libraries are available. And if you see, similarly, if you see about the blockchain, so again, you can see a number of libraries are available. And again, if you see about the quantum computing or any of your area of interest, you can see distributed GPU computing is available, natural computing, and lazy computing. If you click on any of the package, you will see you can download the file and you can get the more project description and the release history, etc., etc. And how to install simple by the pip command. So not only these libraries, many libraries are there. So one can use a PySwift library for secure and private machine learning with PyTorch. And if you are working with directly, you can use a Flower framework or TensorFlow, or the OpenFL is also there, open source federated learning platform. And if you on the search engine, if you write here about the library OpenFL, so you can go to their official website. So this is OpenFL implement ton of useful APIs, and so not only in the intrusion detection or for malware, but also in other applications, one can do the collaboration about this OpenFL, or you can also write here OpenFL federated learning. So you can see OpenFL. So this is a Python-based federated learning framework to train and validate the models on sensitive data. So maybe like on mobile, a lot of malware are coming nowadays. So in this way, they can train the model and send it to the central one. So a number of libraries are available. So in the open source or in you will find a number of libraries are there. So now in this, there are a number of data sets are available, like email phishing data sets are available. You can create your own custom logs, CI/CD or NSL KDD. So in this, we have demo setup. We will have done the pre-processing, define the model, set up the federated learning, and we have trained the model locally on each client, and then use a federated averaging to aggregate the updates, and finally evaluate the global model. So it will test the global model on a centralized validation set to evaluate the performance. So these are the few code scripts are available. So all of you can download. So this data set has been already shared in the Google Classroom. So this is the one of the data set, well-known cybersecurity data set created by University of New South Wales, and it contains real and synthetic network traffic data, include the normal and malicious activities. So for education purpose or for research purpose, one can download and they can develop their own intrusion detection system. So it includes the normal traffic and the malicious traffic, and various features are there. So everything is mentioned in the slides. So kindly go through and now. And if you see the code, so what is the pipeline for implementation of this? So let me show you from here. So now the pipeline is first we need to have the data. So you can get the data from various benchmark data sets are available, like papers with code, IEEE port, and from the research paper or from various uh, research repositories. Then load the data set. So in my case, I have used I have uploaded the data set on the Google Drive, and then we have done the normalization, and then we have defined the model. So you can use any of the model. There are n number of models are available. For this implementation, we have used the convolutional one-dimensional model, and we have defined the architecture. We have assigned the different model. We can assign different models also to the different remote sites, like on the local server or edge devices. We can train the local model independently. So you can train different sites with the different model independently, and then save the train local model for aggregation. And then finally, you can use the train model local model to the central federated learning. So finally, our main objective is to empower the global server. So compute the global server model by averaging the weight from local models, and then deploy the aggregated model. So finally, we can deploy this aggregated model instead of the like model 1, model 2, model 3, model 4, or up to model 10, maybe different model or same model. Finally, we can deploy the aggregated model on the client side. So it will become more powerful as compared to the individual model. So these two concepts are very important. First, to empower the global model, and that model we can deploy again at the client side. And then distribute the updated, like here. So you can read the step 6. So once our model is ready, then we can distribute the updated global model to all remote sites. So all remote sites will become more now powerful as compared to the simple model they have deployed earlier. And we can deploy model in real time for intrusion detection, and we can monitor the system performance and model prediction. Again, we can do the model evaluation, and we can do multiple iterations also. So we can have this environment, and periodically we can retrain the local model with the updated data sets and fine tune with the hyperparameters, and again send it to the global model or the central server. So what we have done, we have uploaded the data simple by using the Google Colab import drive. This is the part of the Google Colab. This will mount the Google Drive. We can verify with the ls command. This is a Linux command, and we can give the complete absolute path. So we can on the Google Drive, when we do the right click on the properties, it will show the absolute path. So we can ls, we can see it is showing the data sets. So there are 5 training data sets and 1 test data sets. Then we can create the directory. This is optional. Why we are doing this? To avoid to write again and again. Instead of writing again the complete, what we are doing, we are copying this data, entire data into one folder done by the name data. So we are creating the 3 directories. One is the data, one as a server, one as a central server. And then we are copying the data with the, again, Linux command. CP is the Linux command recursively. And we are given here star. Star means all files in this folder. And we can verify it again. So now this folder is ready with the all CSV file and with the test dataset. Then we are uploading one local file. This local file is used for the load the data and to do the pre-processing. Then we are using the Keras and TensorFlow library, and from data preparation we have import the load CSV and data set preparation. And then here you can see in the code, remote site 1, the script load the dataset containing the 196 features and 1 label. So 196, that is the independent and dependent variable or target variable. Then we are normalizing the feature for better performance, and we are creating the time lag of 4 to end the model and the pattern over time. So we can deploy any of the models. We are independent for this. So now for remote set 1, we are setting the data. So we have specified the path of the data, and either we can use the pandas dot read CSV file or the load CSV file, and then we are doing the min max scaling, so that we can normalize the data values into in the range of 0 to 1. Then we go for the remote site 2, and same we are reading the data for second remote location, same with the third, fourth, and the fifth one. And after reading that, we are getting the one test data set also. So we have taken the test data set here. So now up to here, what is for 5 remote locations, our data set is ready. Then we are using the TensorFlow and the NumPy library. We are loading the model, and now here we are aggregating the weights. You can see here under the which folder, under server. Under server, we are aggregating the all, and we have defined the architecture here. We have defined the architecture here. Customize, we are compiling it. We are loading the weight and defining the model. So as we have already run the entire code, so if we see the server folder, if we see the server folder, simple will say ls server. Now you can see server 1 dot weights, server 2 dot weights, server 3, server 4, and server 5. So these are the weights are available. So at the final, at the global, it will do the aggregation of these. Then we are defining the model for site 1. So you can define any model. So here, for demonstration purpose, same model we have defined with the convolution neural network with the one-dimensional, and this is the model. This is the we have compiled, and model 1. So similarly, we have done for second, third, fourth, and we are saying here we are saving the weight. So instead of server 1, it is better to give here the name as client 1. Client 1 weights, and similarly we can do for the second one. And here, after running this, we can save as a client 2. Client 2. Client 2. So it will give the better clarity. And same with the we are training, and we are saving the weights. In this way, we are saving the weights. 3, 3. Same with the client 4 and client 5. Client 4 and client 5. Client 5. So now weights not H5. Again, when we are saving, we have various formats are there. So this is one of the format. And then we are collecting here. Now here you can see, I will save this file. So what we are doing here now, under this load the weight of all model in the server directory or in the common directory. So we are using the globe.globe star.weights.h5, match the weight, and it will save all the weights here. And we'll compile it, and we'll do the average of this, average the weight of the loaded model. And finally, we are building the model of the with the. Now you can see here, this is the where we are building the global model. Here we can write here multi global model, build the global model. So now how we will build a global model. So now we got the 5 weights, or for 10 locations we got the 10 weights. So we'll use the average weights. So we are defining here build model, and when we'll.
So can you please tell them to please mute themselves because some extra noise is coming up and we are not we are unable to concentrate.
Dear participants, kindly mute your mic, mute the noise. So build the global model, and again because this is a new concept, again on the notepad I will show you the pipeline and the steps again, and then we are defining the evaluate the model. And we are now here, you can see we are defining the batch size as and here we have defined here batch size we have defined it too long. We will check the okay, let me check how many tuples are there in this file. If I scroll, or yeah, if you see here, we have a sample of approximately 35,000. Around 35,000 are there. So we can make a batch size of, I think some typo mistake is there. So 2,000 batch size we can define. We can evaluate, and so if you see the any of the image processing issue or any problem, or on the kaggle.com or any, more or less the coding is almost same, but the concept here is different. And then finally we are saving the model under central server as FL model, Federated learning model. So here we have given the short name as FL model.h5. This is the flow. So here so in other words, we can say this is also like a future technology. So what are the functions we are calling here? I'm removing other things. We have defined the functions. One is the FL average. This is a build model to build the model with average weights. So in case if we have 10 locations, so we are taking the average of 10 models, and then we are evaluate the model, and we are passing the model and the test data set. This is the test data set and the test labels. And finally we are saving the model. Which model? Global model, or the federated learning model. And we are calling this model in this epoch. Here we have defined the NITTS model that we have created earlier, defined earlier, 1, 2, 3, and we are calling this here under loop. So under loop, simple I'm writing under loop. We are what type of loop? For I in range of epochs. How many number of epochs we want to run? 5, 10, 20. So yesterday we have seen the concept of early stoppage criteria. So we can define here maybe 50, and early stoppage criteria patience value as 3. So what was the concept of that? Suppose I have given here epochs 50 or 100. So at epoch 1, So it will check either for the loss function or for the accuracy. So loss function should decrease and accuracy should increase. So let's say accuracy is 77. I'm considering the epoch 1, epoch 2, epoch 3, epoch 4, epoch 5, epoch 6, epoch 7, epoch 8, epoch 9. And here we have taken the criteria, and it is given in the code also, early stop. And there we are defining the patience value as 3. So now epoch 2, let's say 77.1, epoch 3, 78, epoch 4, 81, epoch 5, 80.5, epoch 6, 80.1, and here 79. So now it will see consecutive. These three are lesser than the 81. So it will stop here. I hope it is clear. It will stop here because we have given the patience. It will check consecutively for the next 3 iterations. So the next 3 iterations are lesser than this value. So it will stop here, and finally it will depict the accuracy as 81. So it will help to control the overfitting. So this is the one criteria. Or so here we have defined the 5, and we are calling the model federated averaging model FL under loop. So loop means we are running this under for a number of epochs. We are running this. And what is epoch? Epoch is the when we send entire data set from the model. So once the entire data set passes through the model, that is known as one epoch. So you have to do the iteration. You have to send data again and again so that model will learn more. So how many epochs we should set? So if you set less, then there is a problem, might be of underfitting. If you say more epochs, it may be a problem of overfitting. So logically, you have to give the appropriate epochs, or you should have used a criteria like early stopping. So now here, when we call this model fit, and this is a model 1, model 2, model 3, and 5. So still we have 15 minutes. So shall I run it again, one by one? Shall we run it again? Then we conclude the
Yes,
session.
sir.
Okay. So now you see carefully. It will not take more than 10 minutes. So I'm again running from the beginning. So I'm going on that again. So this is the pipeline. Please go through these steps: data preparation, pre-processing. We are normalizing it. Then we are doing the model initialization, which model to be select. Then local model training. Then finally we have to. Our main purpose is the train the centralized model, and once the central model is ready, global model is ready, deploy to the end user. That is our aim. So now we will verify it with the ls command. Okay, it is there. So I need not to mount it again. Then we can see the list of directories. Why these 3 lists we are creating? These are optional one, just to instead of writing again and again, because my data is in which file, which folder, content, drive, my drive, collab, under this long path. So to avoid that, I'm simply using the data. So we can now see these are the directories. This is the command to check the operating system version, and we are copying this data to the data folder. And here, when we run this, now these files are available in the data. So we have uploaded this data preparation file. So we can check it again. AID showing here data preparation.py is there. Otherwise, once you download these files from the Google Classroom, you require to upload this. And then we are importing the Globe, NumPy, OS, few libraries. So Globe is required to find the specified pattern, to match the specified pattern. So in our case, it is a CSV files. So these are the remaining files. All descriptions are given here. And for remote site 1, we are simply reading the data and doing the normalization. That's all. Same we are doing with the site 2, site 3, and here also we are defining same we are doing with the site 3, same we are doing with the site 4, site 5. And later on also, if you any of the participants, if they get any doubt or question, they can pose the question in the Google Classroom. We will try to reply. And this is our test data. So this can be kept in a single cell also, or for better clarity, I have taken in the multiple cells. Then we can view normalized data. It's optional. And then finally, we are calling. So why it is running immediately? Because these are the simple functions. Simple functions we are defined. We are defined the model, and you can see here it's still showing the old one, because once we call these functions, it will overwrite and it will show the client 1, client 2, client 3 weights. Then we are defining the models for various remote sites. So this is for the model 1. This is for the model 2, 3, 4, or 5. Now, there could be question, for example, let's say there is a ABC model you have deployed on 10 different locations. So how you will judge the performance, how you will improve that model, because the data will be different. In all 10 different locations, the nature of data will be different. Though the same model is learning 10 different type of data sets. The same antivirus is learning the different locations from different locations, or anti-malware is learning from the different 10, even though the model is same, antivirus or anti-malware is same, but it is learning from different 10 different kind of data sets and sending all the informations to the central one, and it is empowering the this global model. And once the global model is ready, so now global model is ready with the 10 different type of data sets, different 10 types of attacks. So once the global model is ready, again we'll deploy it to the all different clients. So there could be multiple iterations, and the day may come that it will be the client sites or the remote locations will be almost hack proof. So as of today, we cannot say that all banks are hack proof, or so this concept can make them hack proof for the future attacks also, or 0-day attacks also. So now this is a working flow, and this is the epochs we have taken. Now it's running. So as we have less time, let's say I'm taking epochs as only 3. And now we are running it. CD showing FL model exists. So now it will run for 3 epochs. And then finally we get some kind of score in terms of loss and in terms of accuracy. So first value is the loss and the second value will be the accuracy. So you can select the loss function as per the type of problems you are handling. So for regression, for multi-class classification, for binary classification, for probabilistic models or SVM classification, you can use these loss functions. So now I hope you got the idea. So now it's running. We get at epoch 1, epoch 2, and finally in this way we get the output. So now I stop here. Any other question, query from any participant? So kindly download the dataset code and try to run. And in case if you face any issue or any problem, kindly put the query in the Google Classroom. So okay, thank you one and all. So now I stop the presentation.
On the behalf of Faculty Development Program on Digital Forensics for Innovators, leveraging open source in cyber investigations organizing committee, I thank the respected FDP speaker, Mr. Amit, for their valuable talk and hands-on the session. With the permission of FDP speaker, I am concluding the session. Thank you all. Thank you, sir.
Okay, thank you so much. Thank you one and all. Thank you.
Thank you very much, sir.
Thank you.